Okay, I have your quizzes from last time. I have your mini exams also. So I'll just call your name. If you could come up, grab these. And I believe I have one mini exam that does not have a name. At least I couldn't find a name on it. So if you did it and don't get it back, it's probably yours. So just let me know. Alan? Okay. Evan? I think your bonus is in there also. Paras? Jared Booth? Alex Mora? Let's see, Amy? Amy okay. Josh Watson? Katie? It's me right here. James Bustos? Right here. Allie Stanton? Yannick? Clay? Stephen Evans? Oh, wait, sorry. Stephen Evans. Yeah. Okay. Andrea Austin? Andrea or Andrea? Andrea, sorry. Alessandra? Here's the one with no name, so it's like yellow graph paper. That's you. Just see if your name is on there and I didn't see it. Chris Hernandez, David Hernandez, no? Austin Anderson? Did anybody not get theirs back that turned it in? Is that you? Okay, put your name on it, and then I need to put the grade in. Oh, I still have the quizzes. Yeah, here come the quizzes. So, Alex Mora, Amy Castillon, Josh, Yannick. Okay, thank you. Let's see. Jared? Jared? Okay, hold on. This is your quiz. No, that's your test and quiz. Okay. Stephen Evans? James Bustos? Katie? Alessandra? That's your quiz. Let's see here. James Lee? Allie? Paras? Am I saying that right? Yeah, that's fine. Well, how do you pronounce it? Padas. Well, I can do that. I'll try. Let's see. Stephen? There's not here. Clay? David Hernandez? Evan Gonzalez? Austin Anderson? Alan? And that's it. Okay, that's pretty much everything I have. So our test is on Monday. Did everyone get my email that I put up my test from the spring, my exam 1? And I said that I put the solutions up. Well, I went in there and I looked, and the solutions are actually already in there. If you go look through, I don't know what it's under, but it's like, it's in there. One of the folders has a file. It's 2415 exam 1 solutions. It'll say like spring 2014 or something like that. Did you see it? You're shaking your head. So you saw it. So the answers to that exam that I gave in the spring, it's all out there for you to look at. So that's a good place to review. If you do go and look at that exam, you'll notice that most of those problems were pulled directly out of the book, and I think a majority of them came from the chapter review, the chapter reviews for the sections. So just FYI. What else do we have? I talked about last class what you can bring to the test on Monday, right? And we are scheduled on Monday to take the exam. It says we're supposed to take the exam and do 11.8. But that means like I give you some amount of time for the exam, and then after that we continue and we have a lecture. I think it's just going to be, that day is just going to be all exam, okay? And if you finish, you can leave. So, you know, see how it goes. Anything else? Any questions over the exam? You can have how many sheets? 2 sheets with no worked out problems, right? And then you can print out that 7 pages of formulas or whatever, but it's all on the website. You have to do that yourself. Okay? So we're good? All right. Make sure you're on time on Monday, all right? Don't be late to class. Okay, we left off last class. You did the example 6 and example 7 in class as a quiz grade. So that's your first official quiz grade. And we just want to wrap up this section. We had a formula back in, I believe it was chapter 10, where I gave you a formula for finding the equation of a tangent plane to a surface. And you know what? It had to be chapter 11. I take that back. So earlier in chapter 11, we had a formula for it. Well, it turns out that we have a more general version of an equation or a formula for the equation of a tangent plane to a surface. And this will work for any equation of 3 variables, which can be written capital F of x, y, z equals k. So if you think about this, it's an equation that has 3 variables in it equal to a constant. So this would include like your quadratic surfaces, like ellipsoids and paraboloids and all those things, because all of those were equations with 3 variables. The previous formula we had only worked with functions. So we had to have like a surface that was a function of x and y only. So that would not have applied to like an ellipsoid, because an ellipsoid doesn't qualify as a function of x and y. So this is the formula for it. First thing you do is you rewrite the equation so that you get your x, y's, and z's on one side of the equation, and you get a constant on the other side. It could be 0, all right? But as long as your equation is written this way, then the equation of the tangent plane to this surface at some point. So you have to have, you know, some point on the surface and then look for the tangent plane there. If you have a point on the surface, then here's the equation right here. So you'll hopefully recognize that this x minus x naught, y minus y naught, z minus z naught is all part of the equation of plane that we had before, right? Do you remember the equation? Do I need to write it or no? I guess I'll write it. A x minus x naught plus b y minus y naught, right? Remember this? Plus c z minus z naught equals 0. That's the general equation of a plane, where a, b, c is actually the normal vector, right? The components of the normal vector. Remember that? Okay. So this is pretty much, yes. Yeah, you could dot. You could use, the left side as a dot product. Okay. Yes. And in fact, it's, what do we have here? This is our A, isn't it? Our A is here, our B is here, and our C is here. So the A, B, and C are just the partial derivatives, right? partial derivative of the left side of that equation with respect to x, then partial of the left side there with respect to y, and partial with respect to z. And then you have to plug in that point. That's what it means when I say partial of f with respect to x at x naught, y naught, z naught. So you take the partial derivative, you evaluate it at the point on the surface, and that will give you the first component of your normal vector, and then so on and so forth for the next two. Make sense? So since this part up here, the ABC, right, is our normal vector, we can see that it is just the gradient, right? We define the gradient of a function to be a vector that is made up of the components are made up of the partial derivatives. So let's take a look at this example. If we have an ellipsoid and we want to find the equation of the tangent plane to this ellipsoid, then we recognize, first of all, oh, did I give you a point? Yes, there we go. -3, 4, 5. So we notice that we have an equation with 3 variables in it, right? So we can move everything to one side except the constant, which is already the case, isn't it? This right here is our capital F. And now what we do is let's come up with the gradient first, because that'll be our normal vector. So the gradient of this capital F will be equal to what? Well, partial of the left side with respect to x gives us what? 2/9 x. Partial of f with respect to y is just 2y, right? And then partial of f with respect to z gives us 2/25 z. So that's our gradient. Now our normal vector is that vector, but evaluated at the point that we're interested in. So the normal vector for our plane will be equal to, let's plug in the x, the y, and the z in here. So if we plug in -3, what do we get there? -2/3. If we plug in 4 for y, we get 8, right? We plug in 5, we get what? 2/5. Everyone agree? And so now we have a normal vector for the plane, tangent plane, and all we need now is a point, which we already are given, so we can generate the formula, or the equation. So the equation will be the equation of the tangent plane at the point -3, 4, 5 should be -2/3, which is the A, and then x minus x naught, so that'll be for us what? X plus 3, good. And then we have plus our B, which is 8, and then y minus y naught, so y minus 4, and then C, which for us is 5, and then Z minus Z, no, sorry, Z is 2/5. Then Z minus Z naught, which is 5, so Z minus 5, and then equals 0. That's right. The constant on the right will have no bearing on anything here as far as the equation of the tangent plane is concerned. So this is an equation, right? We graph that thing. It's a plane, but it has a very special property. The property is that it should touch our ellipse, and it should be tangent to the ellipse at the point that we are looking. So let's see if it's doing that. So here's the ellipse. I said ellipse. Ellipsoid. Here's the ellipsoid. There's that point. Okay, that's the point that lives on the ellipse. And let me just spin this thing all the way around like this. And then here's the plane. So if I come in here and look at it, you can see that that plane that we found is tangent to the ellipsoid at that point. Okay? Now, The next question that I ask is to find the equation of the normal line to the tangent plane of the ellipsoid at the same ellipsoid at the same point. So let me explain what that is. Let me show you what it is geometrically first, and then we'll go find it. So if you take that same plane that we just had, right, and we had a point going through it, or we had a point that it touched the ellipsoid on, then imagine coming out of that point a line that goes through the plane and it's perpendicular to the plane. That's called the normal line, right? The plane has a normal vector, and if you continue that vector in each direction forever, you create what's called the normal line. So we want to find the equation of that normal line. Well, what do we need for the equation of any line? Vector equation of any line. A point and a direction. Now, do we have the point? Sure. Do we have a direction? Well, the direction is the same direction as the normal vector for the plane, isn't it? So this is really not a whole lot of work to do here. We already have it. This is more just to understand the terminology of what we mean by normal line. Okay, so all we would do here for this one, the equation of the normal line, I will call it R of t. And of course, R of t is always R naught plus TV. R naught for us is the point we're given, but we convert it to a vector, so it's negative 3, 4, 5, plus t times the direction of the line, which is the same as the normal vector of the plane, which was negative 2/3, 8, 2/5. And you can leave it like that, or you can put it all together. Right, that's it. Questions? Okay, that does it for 11.6. Did I give the homework for 11.6 sent out? It did include 11.6, right? Okay, so now let's start 11.7. My goal today is to definitely complete 11.7 and try and get into 11.8. These two sections are extremely heavy. Okay, there's a lot going on here. Yeah, well, I should take that back. There's not a lot going on as far as the theory is concerned, but you have to see a lot of examples to kind of get used to the type of algebra and work that you're going to need to do in order to figure out answers here. And there's a lot of subtleties. So we'll probably get just barely into 11.8 today. Just maybe touch on it. We'll see how we do with this. Okay, so the first thing I'm going to do is I'm going to do a quick little review of some of the topics in Cal 1 from Chapter 4, Section 1, and Chapter 4, Section 3 of your book. And I'm going to kind of do it all very quickly, you know, summarize the main concepts. Back in Cal 1, when you were trying to find, when you were given a function, let's say you were given a function and it did something like that, and you define it, let's say, on a closed interval. Okay? So you define it between 2 points, A and B. So nice continuous function. It's differentiable everywhere, meaning we take derivative everywhere. It's well behaved. If we're looking at on a closed interval and looking at this function, then how can we find the absolute max and min? This will actually help you with, I think, a couple of problems in your take-home test. You have to do this at some point there. I think it's the curvature problem. You have to do something like this. Okay, well, not this, but something that I'm about to review, all right? Find the absolute maximum. So how do we find the absolute maximum of a continuous function on a closed interval? Does anyone remember how we do it? You're in the right chapter. Okay, you are dealing with max and mins there, but that's local max, local min, and that's on an open interval, meaning our domain is not restricted to an interval. If your domain is restricted to an interval, this is the easier of the two cases. If we just open our domain up, it becomes a little more challenging. So it's called the closed interval method. Closed interval method because we're on a closed interval. But what we're doing is we're going to, I guess, realize that if you do have a max and min here, right, the highest and lowest points on this graph, there would be the highest, right? And this left endpoint would be the lowest. So for any function, continuous function on a closed interval, your max and mins, your absolute max and min are either going to occur at the endpoints or somewhere inside, right? And if it happens inside, you know that the slope of the tangent line at that point must be what? 0. Now it could be that you had a graph that looked like this. Oh, terrible. Let me do that instead. So if I restrict that is a continuous function, right? Here my minimum, the minimum value I have is the same as the one above, right? But the minimum value, absolute minimum, occurs at an endpoint. The maximum occurs at the top here, but the slope of the tangent line there is not 0, right? What is it? What's the slope of the tangent line at a cusp or a corner? In other words, what's the derivative of a function at a corner or a cusp? You're shaking your head. Yeah, it's not defined. It's undefined, right? So this right here, up here the slope was 0, so we would say that the derivative up here was 0. Here we say that the derivative is undefined. UND, undefined. Is that okay? So back when we were in Cal 1, we learned that, okay, well, in order to find the absolute max and mins then, what we're going to do is we're going to figure out where our derivative is 0, and we're going to figure out where our derivative is undefined. We're going to call those critical points. So we find the critical points of the function. So we find where f prime equals 0 and where f prime is undefined. We call those critical points. And then what do we do once we find those? Plug them into the original function and also plug what into the original function? The endpoints. So now all you do after you find those things is you plug the critical points, can I call them CP, right? Critical points and endpoints into original, right, function. And when you plug those values into the function, it spits out values, doesn't it? The biggest value you get is your max. The smallest you get is your min. So you plug them in, you compare. And that's it. That's the way that we find the largest and smallest values of a function on a closed interval. Does that kind of ring a bell? A little bit? Okay. So now let's now move away from this. We're not going to do an example or anything here. But let's move away from this and let's look at how we do it if the domain is not restricted on an interval, on a closed interval. So if we have a function, and let's say it does something like this now. You know what? Let me do this. Sorry. I'll make the bottom on a cusp like that. Does this function have an absolute maximum or an absolute minimum? Well, the arrows imply that it keeps going like that, right? Forever. So this thing goes down forever. This one goes up forever on the right side. So this function appears to not have an absolute max or an absolute min, right? There is no highest or lowest value. But there are some interesting values within the function. Here we have what we call the local, right? A local max. And here we had what? Local min. Right? Locally, it's the lowest point. Locally, the other one's the highest. So how do we find local max and local min? Well, that's where we could bring in the derivative, the second derivative test, right? What we could say is this. For this one right here, what's the slope of the tangent line? 0, right? And then, if you take the second derivative, it's concave what? Down, right? So I'll put in here, I'll do it in black. We would be like that, concave down. So second derivative is negative, right? So if we have, if f prime at some value of a is equal to 0, and f double prime, not plus, and f double prime at a is less than 0, then we have a local max at x equals a, right? So if there's some point where our first derivative is 0 and our second derivative is negative, we know for sure that's a local max. How about if we have first derivative is 0, second derivative is positive at some point? What do we have? We have a local min, don't we? That would look like this. If I draw a function that does this, maybe it does that right there. This point down here, the slope of the tangent line is 0, and then if you do second derivative, it's concave up like that. So we have a local min at x is a. What about that cusp? What about that cusp right there? What's happening there? It's undefined. Now the second derivative test that this right here is a second derivative test from Cal 1. But the second derivative test requires that your first derivative is 0 in order for the test to work. So at that cusp, I do not have the second derivative test, can't use it. But what could I still do? There was another kind of approach you could use. Pardon me? Yeah, exactly. What we did is we said, okay, look, if the derivative at some point is undefined, right, then what we could do is we could check to the left of it and to the right of it and look if our slope of our tangent line is going down and then up, or if it's going up and then down. So what we do is we look at test points and we check for change in derivative from positive to negative or negative to positive. So I'm not going to really show a lot there, but just notice on this one, if you were to look on the left side of this curve, which is there in green, if we were to look in here, then take the derivative anywhere over there, our tangent would be negative, right? So I'm going to put over here, our derivative here would be negative. But if we go to the other side of the line, take something over here, or not the line, that point, the derivative over here would be, first derivative would be positive. So as long as your function is defined at that cusp, and your derivative at that point is undefined, and your derivative goes from negative to positive, you know that that's a local min. And if it went the other way, went positive to negative, then it was a local max. Okay? All right, that's just a reminder of how things worked. So I'll put under here, you have to check left and right. All right, with that in mind, let's take a look at what we're going to do today. So now what we're looking at are surfaces. Now this may or may not be in your notes. This is not there, picture? This is not in your notes. So I never added this whenever I did the printout. I apologize. But there's not a whole lot here that you really need to put down. So that's a picture of this weird looking dimply surface, right? And if we look at this surface, we could argue that it has it appears to have an absolute maximum up here, right? And this looks like not the biggest point, but it looks like maybe a local maximum. And then we've got another one there in the back. We've got some smaller little hills here, and maybe there's one here. And then if you look at it from the bottom, we've got some local minimums, and then it looks like an absolute minimum there, right? So the question becomes, how do we find points like this on a surface? That's just zoomed in there. So this is straight out of your book. I don't know what page this is, but this is that same picture that I just had up there. We call this an absolute max. We call this a local max, local min, absolute min, right? And here are the definitions straight out of the book. A function of two variables, so a surface, has a local maximum at some point if it's basically bigger than every point near it. So king of the hill, right? It's the highest point around. Everyone around it's below it. And when we say near AB, that's where we get into like, well, what does near mean? And we won't get into that. And then we have to kind of get some terminology clear here. If we say we have a local maximum, right? The local maximum happens at a point, but the actual value, the maximum value, is the function's value at that point. They're two different things. We go back up here. I like this picture better. Right there at the top of the hill, there is a point in the domain, right? In the XY on the floor that you plug in that goes up to that. The point on the ground, we call AB, is where the maximum occurs. F of AB is the maximum value. What I'm always going to ask you for on a test is not for you to give me the point that it happens and not for you to give me the value separately. I want you to just write down what F of AB is. So that way I can see that you have the point and the value together. You'll see once we do examples, but I want all the information in your answer. Okay, so just like in Cal 1, we have tests, all right? It turns out that our tests here work out a little bit nicer than the ones that we had. Well, at least for this scenario, it works out a little nicer than what we had in Cal 1. So let me ask you right now, for this function, does it appear that I have restricted the domain? So go back over here. Remember, this was Cal 1, no restriction on domain, right? We could find local max, local min. Restriction on domain, we could find absolute max, absolute min, right? So here, no, not here. Here, have I restricted the domain? Well, it looks like I have because I've cut it off and it looks like this square, right? But I haven't told you I restricted it. So what we're looking at right now are surfaces with unrestricted domains. All right, unrestricted. So imagine that this goes out forever in every direction. The next thing we'll do after this is we will restrict the domains, but it turns out that that's harder to do than this, so we do this first. All right? So right now we have an unrestricted domain, or you could say it's the implied domain of the function. If you look at trying to find the maximum and minimum values, the local max, local min, on a unrestricted domain, then here's what we use. There's a theorem here, but it's really not that big of a deal. We'll just pass over it. The second derivative test is the big thing. Suppose the second partial derivatives of f are continuous on a disk with center AB. And suppose that the partial of f with respect to x at that point is 0, and the partial with respect to y at that point is 0. So you basically look at this picture we had here, right? Look at this picture. And imagine if we we did a partial derivative, we're cutting it with the plane, aren't we? And then we would have a curve. That would almost just look like a parabola on the top of this curve, wouldn't it? And then if we say that the partial derivative must be 0, it means we have a flat tangent line. And then if we cut it with the other plane, the other perpendicular to it, and take that curve, and that derivative, partial derivative being 0, means we have another flat tangent line, which means we have two flat tangent lines, which means we should have a flat tangent plane, which means we should be at a max maybe, or maybe a min. So that's what the first condition of this says. You first have to have that the partials are equal to 0, right? If both partials are equal to 0, then the way to figure out whether or not you're at a max or a min is that you have to compute this thing called capital D. And capital D, at that point, is the second partial with respect to x times the second partial with respect to y. Multiply those two answers together, subtract the partial with respect to x, then y, figure that out, and then square it. If this answer, D, is a positive number, and the second partial with respect to x, this right here, fxx, if that was positive, then you're at a local min. If D is positive and this one is negative, then you're at a local max. If D is negative, then you're not at a local max and you're not at a local min. You're at what's called a saddle point. Okay, so remember the thing I'm trying to make a connection with here is this right here. We had, with unrestricted domain, the second derivative test said we have the first derivative has to be 0, right? And then the second derivative gives us concavity, up, down. Very similar to what we're saying here. We're saying that the first partials have to both be equal to 0, right? So flat tangent lines. And then you have to compute this D, which works with the second partials, which is almost like the concavity part. Okay, now you may ask, like, well, how is this true that if you multiply this and this, how is this going to give us that? There's a proof in the back of the book of why this works. They only prove it, and it's pretty easy to follow, I think. They only prove it for the first case A, but then case B can be done the same way, and then case C. So if you look through that, if you want to know like where this comes from, you can. Question? Mm-hmm. It doesn't account for all other directions. I tell you what, look at the proof, because I read through. I think the proof will help, because the way it's set up, I think is pretty a natural progression of things, and they do it more algebraically than they do geometrically. But I think you can make the geometric connections when you look at the proof of what this is. All right. I'm not sure I follow you. Are you saying like you could set it up and it's like a determinant of a matrix or something? Okay. I suppose you could. You could probably rewrite a lot of things as a determinant of a matrix. Okay. All right. Well, for now, we'll just go with this. All right. Okay. All right. So let's try and find the extreme values of this function f of x, y. Extreme values means we want to find local max, local min. Okay. Extreme values is another terminology used for local max, local min. So first things first, has there been a restriction put on the domain of this function? Doesn't look like it, right? I mean, just there's the function right there, boom. So we want to know the highest and lowest points. Take a look at this right now. Does it look like we have a highest and lowest point? I've already graphed it for us here. Remember, there's no restriction, so this thing continues to do this in each direction forever. Does it appear that we're going to have a highest and lowest anywhere? Doesn't look like it, but let's see what the algebra does, how the algebra works out here. So we're starting off f of xy is y squared minus x squared, right? So we have a function of two variables. We're trying to find extreme values. Unrestricted domain, I'm going to use the second derivative test, which means I'm going to need the first partials, right? I'm going to need the second partials. I need a lot of derivatives here, right? So you can, if you want, just kind of work all the derivatives out first and then just try and play with them after you've got them all. Okay, since you know you're going to need them. So let's just list them out here. What's the partial of f with respect to x? Negative 2x. And then we're going to need derivative of that, right? With respect to x again. What's that? Negative 2. Okay, I also need the partial with respect to y, which is 2y. And the partial with respect to y again, which is just 2. But I also needed the partial with respect to x and then y. Don't I need that in the formula for D? Okay, so what's the partial of f with respect to x and then with respect to y? 0. All right, so those are all the derivatives I'm going to need. I'm just going to leave them over here. I'll come back to these when I need them. Now, what we need first is to figure out the points A and B, right? I need to find, if there are any points A, B, such that the first partial at that point is 0 and the first partial with respect to y at that point is 0. So if you go back to the notes, what I'm doing is I'm trying to satisfy this first condition of the second derivative test. There's some point that when I take the first partial with respect to x, that it's 0, and that first partial with respect to y, I get 0 also. Once I find that point, then I go compute what D is. And there may be more than one, right? So let's see what we get here. So solving this equation, when is the first partial with respect to x of this equal to 0? Well, that means first partial, that's negative 2x, that equals 0. There's only one solution to that, right? X is 0. Now, the first partial with respect to y, if I set that to 0, that means I'm setting 2y equal to 0, and there's only one solution to that, which is 0. So the only way to satisfy the two equations is if I let x be 0 and y be 0. So I only have one point, right? One critical point is what we'll call it. The one critical point we have is the point 0, 0. Now I compute D. All right, so let's do our computation of D. D is going to be equal to the partial with respect to x twice at 0, 0, partial with respect to y twice at 0, 0, minus the partial with respect to x, then y at 0, 0, and then take that and square it. Now, does it even matter? I mean, when this all works out, does it even matter that I'm at the point 0, 0? I mean, look at what is the second partial with respect to x? What is it? It's negative 2. It's independent of anything, right? Does not matter what my x and y is. It's negative 2. So the fact that that's negative 2 here means that this part right here is just negative 2 times, and then same thing happened with second partial with respect to y. That's a 2. And then minus my partial with respect to x, then y, is just 0, right? Again, independent of x and y. So it's just 0 squared, which doesn't matter. It's still 0. So what does that give me? Negative 4, which means it's not a local max, not a local min, right? D is negative. If D is negative, you don't have it. You have what's called a saddle point. Okay, so here's what we'll say. Since D is negative, f of 0, 0 What is f of 0, 0? Plug 0, 0 into the function. Into the original function up here. What does it spit out? It spits out 0, doesn't it? Is a saddle point. Another way you could write this is this way. 0, 0, 0 is a saddle point. See, 0, 0, 0 lives on the surface, doesn't it? And I'm saying that that is a saddle point. Do y'all see why they call it a saddle point? Do y'all see? What's that? Looks like a saddle, right? That's what a saddle on a horse's back would look like, kind of. So what's happening in this saddle point, if you go to the origin, which is right there where my cursor is, in one direction, it's like a concave down, and then if you turn perpendicular to that, it's concave up. So you get the saddle point. All right, that's about as easy as they get, right? Because your second partials were constants, and it just all worked out. So let's take a look at something that's a little more complicated. Looks like we have what here? As far as points are concerned, what does it look like we're going to get here? Local mins? And anything else? Maybe a saddle at the origin right there? Kind of hard to see. Very proud of everyone in here. Last semester, I don't think my students could hold it straight when I showed this function. So, you did a good job. Okay, so what's the function here? All right, so let's create the list of things we'll need, right? And this is very computational, isn't it? I mean, there's not a whole lot of, I guess you have to think, but it's very mechanical, isn't it? Just take derivatives and then plug it into a formula and then get results. The hard part will be the algebra that will be required. I mean, and that's not necessarily the hard part, but that's the part that will become somewhat of a challenge. So let's go ahead and take our partials. What's our partial with respect to x? 4x cubed minus, what is it? 4y, okay? What's our partial with respect to x again? 12x squared. Okay, what's our partial with respect to y? 4y cubed minus 4x. What's our partial with respect to y again? 12y. Which other one do I need? xy, right? Is it? Yes, it is. Thank you. Partial with respect to x, then y. What's that? Negative 4. All right, so that's the information I will need for this problem. And now I need to try and figure out if there are points, A, B, right, and there might be more than one, that make my first partials equal to 0, right? So that's what I need. I need to find points that make that happen. So what I need is to set my first partial equal to 0, which means I set 4x cubed minus 4y equal to 0. Now in the last problem, that was a very easy equation, wasn't it? And we just said, oh, well, y is 0, x is 0, whatever it was. This is not so easy. In fact, you have one equation, you have two variables, so you cannot find a unique solution to this. So that by itself is not enough information. We need to bring in that other partial and see what it says. So what about the other partial? We need that to be equal to 0, so we need 4y cubed minus 4x to be equal to 0. And that one we cannot find a general, we cannot solve for a unique solution for that one also. So any ideas on what you can do? You could set them equal to each other because they're both equal to 0, right? You could do that. Any other ideas? I mean, that's not wrong, but I'm just saying what other ideas you might have. Okay, so like solve one of the equations for, like, let's say y, and then substitute into the other equation for y, couldn't you? Because both of the, whatever x and y make these true, have to make them true at the same time. So whatever y is in the first one has to be the same y in the second one. So let me just show you, well, you pick. Which way do you want to go? You want to set them equal to each other? I mean, that's the first thing I heard. You want to try that? It looks easier to make y equal to something and then substitute? Is that what you're saying? What you're going to learn, I guess, by doing practice on this is that sometimes one way is better than the other. It just depends on the problem. It's not there's not like a cookie cutter way you always do it. This is algebra, so you just got to grind it out. However, sometimes it works out hard, sometimes it works out easy. It just depends. So your approach matters here. Let me try the zero, setting them equal to each other just so we can see where that would have led us. Okay, so let me try this. I'm going to try, what's that? No? I know it won't be as good, but it's good to see why it's no good. So if I were doing this problem, first thing I would have done is just divide everything by 4. Right? And then what? Yeah. Do what? Oh, you just thinking of a solution? Yeah, you can just mechanically do it, right? This brings up a good point. Remember on the take-home test where I had you solve that that 4th degree polynomial using rational zero test and synthetic division? That's what I wanted. And some people were able to just like think what the answer would be or try some answers. You have to keep in mind that a lot of the problems that we present in a class, the solutions are nice solutions just to keep the algebra of things and everything nice, right? So it works out. So like right here, we get a solution. We can kind of see one would work. But in the real world, your solutions are very rarely going to be nice integers and things like that. So we are more concerned about technique than we are about just taking a swing and we get it. Now, sometimes it's a good method. I mean, because sometimes you don't want to make it overcomplicated. Shit, if one works, it works. But is that the only answer? That would be the concern. So let's just try this. How about if I bring everything over to one side? Could I do this? Just kind of order it this way? Yeah? Could I factor the difference of cubes in the front like this? Plus 1. No, plus y squared, sorry. Y'all know what I'm doing there? That's just factoring this right here. And then I still have here plus x minus y. That must be equal to 0. And then I could factor out this, couldn't I? They're in both. So I could pull out an x minus y. And I could say times whatever was left here. So I had x squared plus xy plus y squared. Then what? Plus 1, and then all that equals 0. And then I could set those both equal to 0, couldn't I? Now this one's easy, because if I set that equal to 0, I get x is y, don't I? X must equal y. Now what about setting this one equal to 0? That's a little more involved, isn't it? And so maybe at this point is the point where I would say, you know what? I mean, I was able to get one possible answer here, but this seems like it's not really, I don't want to go down this road. Has anyone seen how to solve something like this? Solve it for x using quadratic formula? Y'all ever seen that before? There's a way of doing it. I don't want to get into it because it'll take us probably 20 minutes to do it. But if you have an equation like this, I have like an x squared, right? So I have like a like an ax squared, and then I have this. This is like a bx, but my b is actually what? My b is y. And then all of this together, I could act like that's my c. So I have ax squared plus bx plus c. So if I use quadratic formula, the solutions to that being 0 are x is negative b plus or minus square root of b squared minus 4ac all over 2a, where a is just 1, b is y, and c is y squared plus 1. If you do that, you can solve that for x. Well, it's not. You're not assuming. You're assuming y is something, right? What it does is it gives you an equation where x is solved, like you've solved for x, and it depends on only y. So it can be done, but it's definitely not a road that I want to go down here, all right? So instead, let's try that other method. The other method was to take one of those up there and solve it for y. Divide both sides by 4, is that okay? So you should get y is equal to x cubed. And then this equation here tells me what? If I divide by 4, I could say y cubed equals x. Agree with that? Now, if y is x cubed, then I can take this x cubed, I can plug it right in here for y, which means I have x cubed cubed equals x. Do you agree? That's the same as x to the 9th equals x. And how do we solve that? Yep. The biggest thing here, the mistake that I see whenever people have equations like this, is they divide by x. Okay, if you divide by x, you're going to eliminate a possible solution. Because when you divide by x, you're saying x can't be 0, but 0 is a solution to this. So the best way to do it, or the proper way to do it, is to move everything to one side. And then factor out an x. And now set each of those equal to 0. All right, the first one is just 0. The second one says x to the 8th must be equal to 1. And how do you solve that? Take the 8th root of x to the 8th on both sides. What do you have to do when you take the 8th root of something? You have to do plus or minus. In fact, you have to do plus or minus anytime you do any even root on both sides of an equation. So you're going to get x is what? Plus or minus 1. So we have 3 possible x values that make this thing work. We have x is 0, we have x is 1, and we have x is negative 1. So in terms of critical points, I know that I can have my x be 0, I can have my x be 1, and I can have my x be negative 1. And then how do we get the y coordinates of those? Into what? Into where did we have a relationship between x and y? Okay, when you said original, were you talking here? Yeah. Okay, yes. I thought you were talking up here. Okay, yes. Anywhere we have a connection between x and y, we can plug it in. But this one's the easiest, right? I have y is x cubed. So if I plug 0 in here for x, I get 0. So I know this is going to give me 0. If I plug 1 in here for x, I get 1 cubed, which is still 1. And then if I plug in negative 1 cubed will also give me negative 1. So those are my 3 critical points, which kind of match what we said, right? It looked like we had 2 local mins. It looked like we might have a saddle. Well, we have 3 critical points, so it kind of makes sense that this is happening. Now what? I need to compute D for each of those points, right? So let's first write down what D is. D, right, at some point AB is equal to the second partial with respect to x at that point times the second partial with respect to y at that point minus partial with respect to x then y at that point, all that squared. Now, what is the partial with respect to x twice? Up there we said it was what, 12x squared? Okay. So I'm going to put here 12x squared. Now, I'm getting a little loose with my notation there. This should actually say 12a squared because I'm treating my x like it's an a. Do you all understand that? You could come back here and replace xy, 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 xy. And then times partial with respect to y twice, which was 12y squared. And then minus partial with respect to x then y, which was what? -4. And then squared. Okay, let's try first 0, 0. At 0, 0, d will be equal to what? So we're plugging in 0 for x and 0 for y. So that just kills all that off, right? 0 times 0 minus what? 16. That's -16. That's less than 0, which means that we have a negative d, which means we have saddle point. And where's that point? F of 0, 0, which is what? So we have to go back to the top here. You plug in 0, 0 in here, you get 1, don't you? So if you like, you could say at 0, 0, 1, you have a saddle. Make sense? And now we need to compute d for the other two. Next page. I have to go to a new page here. So at 1, 1, our computation of d will be what? 12 times 1 squared, right? Which is 12 times 12 times y squared. Y is 1 also. So 12 again, and then minus 16. That didn't change, right? So what is that? Well, it's a number. It's positive, isn't it? So our d is positive. Now, what happens if d is positive? Now you have to, if d is positive, now you have to go look at what? Yeah, look. This note said, if your d is positive, then you have to go now look at your second partial with respect to x and see if it's positive or negative. That's how you'll be able to determine local max and min. So let's look at our second partial. Our second partial with respect to x at the point 0, not 0, 0, at 1, 1 is just, it was 12x squared, right? So if I plug in 1 there, which is just 12, that's greater than 0. So what do we get? Local min. Local min. Is that all right? So we have a local min. And where is it happening? Well, f of 1, 1. What is f of 1, 1? Is it -1? So if you want, you could say it at that point right there. You have a local min. Now, what if we do -1, -1, which is our last critical point? D should also be greater than 0, right? It's going to be the exact same computation because when you square -1, you'll still get 12, 12. But then our second partial with respect to x at -1, 1, well, does that change? No, because you're still squaring the -1, so you still get 12, and it's still greater than 0. So you'll also have a local min here. and it's -1, I believe it does still turn out to be -1. Someone can check that, but I'm pretty sure it's right. Any questions? Sure? Yeah, it is. But it's pretty powerful because, I mean, if you have any function of two variables, as long as it's well behaved, then you can find highest and lowest points. So just like in Cal 1, I don't know how much application you did, but any function, whether it be like a business application or a physics application, you can always find where you have these highest and lowest points. And a business might say, okay, we want to know when that happens, right? So we have a way of doing it. Or like, what's one of the like classic Cal 1 problems where you're like trying to create, maybe you're trying to make a cylinder, and you want to make a cylinder so it holds, let's say, a liter of whatever, but you want to use minimum surface area so that you don't have to use as much material. Well, that just comes down to finding the minimum of a function of one variable, right? Do you remember how these problems were done? Like you would get area in terms of just one of the variables. Well, you could do that problem now, and you would not have to get area in terms of one variable. You would only have to get area in terms of two. If you get area in terms of two, then you can do what we're doing now instead of doing what you did in Cal 1. And it reduces the amount of work tremendously. I don't know if that makes sense. Kind of getting ahead of myself a little bit because we will do application of this a little bit later. All right, so let's see. Next example. Let's see how involved the next one is. Yeah, this one won't take too long. Let's take a look at that one. So f of xy equals x cubed y plus 12x squared minus 8y. Trying to find the local max and mins of this. So partial with respect to x, what do we got? 3x squared y plus 24x. Y'all agree? Partial with respect to x again, 6xy plus 24. Partial with respect to y. What's that? X cubed minus 8. And then partial with respect to y again is 0. Oh, I like that. And then what's the partial with respect to x, then y? 3x squared. That's it. So we got to be able to pop those derivatives off pretty quickly, and then we'll use them in a little bit. So now I need to figure out what makes my partial with respect to x equals 0, which means I need 3x squared y plus 24x to be equal to 0. So how can I make that 0? Well, again, I don't have a unique solution, do I? I have x's and y's. So let's just look at the other one, see what it looks like. That one is x cubed minus 8 must be 0. And do you like that one? Absolutely. It doesn't have a y in there, so we should be able to find a solution to that. You could just visually see it, hopefully, right? What cubed minus 8 gives you 0? So algebraically, that's what we're doing. Cube root both sides. When I do cube root, do I have to do plus or minus? On cube root, do I? No. On cube root, do not have to do plus or minus. So I only get one solution here of 2. So I already know what x has to be, right? X has to be 2 no matter what. And so to figure out what the y value must be, I can go back up to the first partial with respect to x and just replace my x's with 2's, right? So I'm going to grab this one. I'm going to say 3 times 2 squared y plus 24 times 2 must be 0. So 2 squared is 4, times 3 is 12, so 12y plus 48 must be 0. So y must be what? 4, negative 4. Agreed? So I only have one critical point. So I need to calculate d there. So let's see if I can put d here. And let's just try it all at one time. D of 2 negative 4 will be equal to my second partial with respect to x, with 2 being plugged in for x and negative 4 being plugged in for y. So what happens if I plug in 2 here and negative 4 here? Negative 48. And I'll put negative 48 plus 24, even though we could put that together. Everyone understand where that came from? And then we need partial with respect to y twice. Oh, crap, we should have seen that a long time ago. What's that? 0, it doesn't even matter. What does that tell me right now? As long as this piece right here doesn't turn out to be 0, it has to be negative, doesn't it? That last part? So it's this, and then now I need partial with respect to x then y, which is 3x squared. I need to plug in 2 there, right? So that'll give me a 12. And then I square it. And that's 0 minus 144, so that is a negative number, isn't it? So we have a saddle, don't we? We have a saddle. Now, something subtle here we haven't talked about. What if d is 0? We've said what happens if d is negative. We've said what happens if d is positive, then we have to go check that second partial, right? But what if d is 0? It's actually inconclusive. The test fails. So that means it just doesn't work. The test doesn't work. I believe there is a problem that we will run into that is going to happen. So we'll deal with that when we get to it. So I say here we have a what, where? Saddle point. Where do I have a saddle? At 2, negative 4. And then you have to plug that in, don't you? Into the original problem. Does it come out to be 48? What's that? 2 here, 8, negative 4. That's 12 times 4 minus 8 times negative 4 there, right? No. Negative 4. So what's that? 48? I think it's 48. These two cancel. So we should get 48. So go back to my picture here. Oh, it actually has the point that it's right there on the graph. Do you see it right there? It's that point right there. All right. Take a look at this one. See how many more we got of. Jesus. We have, let's see, 1, 2, 3. There's still 4 more examples. Let me see what the algebra of this one turns out to be. Yeah, let's look at this one. I hate to skip it, but I think it's worth us seeing how nasty some of this becomes. So if we have f of xy is e to the 4y minus x squared minus y squared, we're trying to find the local maximums and minimums of this. And the picture of this one is just like this pimple, just sitting there. There it is. Okay? Just a single mound on this surface. So let's go try and find where that happens. So I'm going to need the partial with respect to x first, right? So partial with respect to x. Well, the derivative of e to anything is itself, right? So we get e to the 4y minus x squared minus y squared. But then times chain rule, derivative of what was up there with respect to x. What's the derivative of what's up there with respect to x? Negative 2x. Now, I guess we'll go and we'll clean that up a little bit. This negative 2x e to the 4y minus x squared minus y squared. If we take the partial of that now, again with respect to x, we have what happening? Product rule. So we've got a product right down there, so we got to do that. So derivative of the first one there is negative 2 with respect to x, right? Negative 2 times the e to the junk. Now, I'm going to get lazy. I'm just going to put a box there to represent all that junk up there, okay? And then I have product rule says plus the derivative of the e part of it, right? Well, the derivative of the e part, isn't that the same as this right here? Right? Isn't that this again? Because that's, you know, derivative of this is what we're trying to find, which turned out to be this. So I'm going to just rewrite negative 2x times e to that junk, right? Times what, though? The first part of that, so negative 2x again. And if I clean that up a little bit, I get negative 2e to the junk, and I have plus 4x squared e to the junk. And if I factor out an e to the, well, let me factor out, how about a 2e to the junk? Is that okay? A 2e to the junk, I will be left with what? Negative 1 plus 2x squared, or I could say 2x squared minus 1. Do y'all agree? So, so far, the moral of the story on this one is that our partial derivatives aren't as clean as they've been. They're requiring a little bit more chain rule and keeping things in order. All right, what about the derivative of this with respect to y? All right, I'm going to put it right here. What's the derivative of this thing with respect to y? So you agree it's e to that junk again? But then times the derivative of the junk with respect to y, which is 4 minus 2y, isn't it? And so I could rewrite that as 4 minus 2y times e to all that. And now I'm ready to do the second partial with respect to x. I mean, with respect to y. So product rule again, right? What's derivative of the first part there? Negative 2, e to the junk. Then plus the derivative of e to the junk with respect to y again, which is exactly what we had before, right? It's this again. Are you all okay with this? I mean, it's a little tedious, but there's nothing crazy here, you think? Just got to keep track of things. So that's the derivative of this, and then times what? Yep, so it'll be that thing again. You want to just throw a squared on there? It's fine with me. And then you can factor out what there? Let's just, how about we just pull the, just the e to the junk out instead of trying to grab a 2 out of there. Let's just go e to the junk comes out. We'll be left with the 4 minus 2y squared, then minus 2. Is that okay? When we were doing product rule here, the derivative of this was this, negative 2 times that. And then derivative of this is this, right? So that goes here. And then to end product rule, we had another one in the back, and we just move it out in front as a squared. And what's the last one we need? Partial with respect to x, then y. So here's our partial with respect to x right here. We need to do the derivative of this with respect to y. So do we have product rule? No, because x is like a constant. So we'll leave the negative 2x out here. And then we do derivative of the e thing with respect to y, which is this answer right here. So we should get 4 minus 2y e to the junk. So we have our partials, don't we? All of our partials. Whew. What's the first thing I have to do now? Now that I've done all that, figure out when the first partials are equal to 0, right? So here I go trying to do that. All right, so let me try and set my first partial equal to 0, which means I'm setting negative 2x e to the junk equal to 0. Is that all right? Now, e to something can never be 0, right? Exponential functions cannot be 0. So I don't even have to consider that. I could even just divide it out on both sides and it's gone. So all you have is negative 2x equals 0, which means the x must be 0. Is everyone all right? Comfortable with the idea that e to anything can't be 0? Yes? Okay, the other one, equals 0, is this one up here. And that's going to give us the same sort of story. We have 4 minus 2y, e to that stuff must be 0, which means that 4 minus 2y must be 0, which means that y must be 2. And then that means, fortunately for us, we only have one point where this one critical point, the point is 0, 2. So my critical point is 0, 2. And now I need to compute d there. All right, here we go. Where's fxx? Well, that's this, right? And I need to plug in 0 for x. Well, unfortunately, I got real lazy, so I don't know what that e to the junk gets me when I plug in. Sorry, 0 for x and 2 for y. I need to plug in 0 for x and 2 for y up here. What happens if I plug in 0 for x and 2 for y? So I get 8, right? 0, and then here's 2 squares 4, so you get what? 8 minus 4 is 4. So you get 2. Are you all right with that? 2 to the 4. We still have back here 2x squared minus 1. This is just going to be 2e to the 4, right? And then this with a 0 right there is going to give us negative 1. So you get negative 2e to the 4th. So negative 2e to the 4th. And then times, now do the same thing here. Second partial with respect to y, which was here. What did e to that junk give me when I plugged in 0 for x and 2 for y? It was e to the 4th, right? And then what do I get here when I plug in 0 for x and 2 for y? Well, only 2 for y, right? 2 times 2? 4. 4 minus 4 is 0. 0 squared, 0, but then I have negative 2. So I have negative 2e to the 4 again. Minus, and now I come down here to fxx. fxx, when I plug in 0 for x, I'm done, aren't I? Because as soon as I plug in 0 for x, this whole thing goes away. So I get 0 squared. And that is positive or negative? Positive number. And because it's positive, now I have to go and check that second partial. Isn't that just this piece right here? Isn't that what that is? And it's negative. So if you have positive d and negative fxx, then you have local max. So we have local max. It happens at the point 0, 2, and then let's actually figure out what that is. So we have to go way back up to the original function and plug in 0 for x and 2 for y. We already know what happens there, right? It's e to the 4th. So we get e to the 4th. There we go. I think the next one is really a pretty good one. So I think that it's safe to say that all of you probably have caught on to the method, right? Is that safe to say? You all know what you're supposed to do, right? Find the partials and then set the first ones equal to 0 and then try and solve and then plug those in and calculate like the method should all be okay. It's just, like I said, it's the manipulation of things, the little signs that you can make mistakes on, you have to be careful with. These are types of things that if you mess one little thing up on the test, right, way up in the beginning, it could really make a big difference. So you got to be careful. All right, here we go. Partial with respect to x. Well, before I do that, I recommend we kind of rewrite this. And I would probably rewrite it 2 ways you could rewrite this. I'm going to bring the x squared, y squared up. You could bring it all up as an x, y in parentheses to the -2, or you could do them individually like that. It doesn't matter. They both give you the same thing. That's the way I'm going to write it. And now I'm going to go do my partials. So partial with respect to x, I treat y like a constant. This gives me 2x, and then what? So I'm taking derivative right here. I'm treating y like just a number. What's derivative of x to the -2? -2x to the -3. And I still have next to it y to the -2, don't I? And now do the partial again with respect to x. That gives me 2, what then? Plus 6, x to the -4, y to the -2. See how clean that derivative is if you brought those things up? Right? If you leave them down there, do like quotient rule or something, you're going to be there for a while. All right, now let's do the fy, which would be practically the same thing, isn't it? I mean, it's almost identical. It'll be -2 y to the -3 x squared, x to -2. And then fyy is 2 plus 6 y to the -4 x to the -2. And then what's fxy? Four x to the -3, y to the -3. There we go. So first thing I need to do is try and find out what makes my partial with respect to x and my partial with respect to y 0. Partial with respect to x equals 0 means I need to figure out when 2x minus, how about if I rewrite it this way, 2 over x cubed y squared equals 0. So now I've gone and I've rewritten the partial with respect to x back in kind of a fractional form. And I've done that so that I can get a common denominator and put these two together, these two terms on the left together. So if I do that, what do I have to introduce on that fraction on the left, on the bottom and top? X cubed y squared, right? So it's going to become 2x to the fourth y squared over that denominator x cubed y squared minus 2 over, and then the whole thing is over x cubed y squared equals 0. And now what I can do is I can multiply both sides by the denominator, the x cubed y squared. Is that a legitimate algebraic move there? Is it legal for me to multiply both sides by x cubed y squared without being concerned about anything? A fraction can only be 0 if what? If the numerator is 0, right? No matter what. Unless your denominator at some point is 0, then it's undefined, right? I think it's pretty obvious to see where it's undefined. Where is this thing undefined? At 0, 0, right? At the origin? But the original function was undefined at the origin, right? So 0, 0 is not even in our implied domain. So we don't even have to really consider that, but it's something we should pay attention to a little bit. So I'm going to go ahead and wipe this thing out. And so I'm really just trying to figure out when 2x to the fourth y squared minus 2 equals 0. And for that, what do you think? Do what? You want to work with the other one? That's fine with me. Can I do this first, though? Can I just divide both sides by 2 first? And then do you mind if I bring that one to the other side? Is that okay? I could do that, right? All right, now let's look at the other one. Partial with respect to y, let's set that equal to 0. Well, isn't that pretty much the same damn equation? I mean, it's almost identical, right? Except it's y cubed x squared down here equals 0. Isn't it? And so if I go and I use the same logic and work through the problem exactly the same, what should I get here after I work it through? I should get y to the fourth x squared equals 1, right? Shouldn't I? You mean like square root on both sides? Is that what you're saying? Well, what I'm going to do is I'm going to set these both equal to each other at this point. You could, though. I mean, you could take a square root, but the problem is you would still have y squared x equals plus or minus 1. You know what I'm saying? You haven't solved for what x is and what y is. If we set these equal to each other, let's see what would happen. Like I said, there may be other ways to get to the same result I'm going to get to here. I'm just showing you, one approach. Since they're both equal to 1, I set them equal to each other. Is that fair to say? And then I'm going to bring everything over to one side. And then now I'm going to pull a GCF out. So what would be a GCF? X squared, y squared. And what would be left? X squared minus y squared equals 0. And then we notice that x squared minus y squared is the same as x plus 1 times x minus 1. Difference of squares. And now you have 4 equations, right? You have x squared is 0. Y squared is 0. The other one is x plus y equals 0. And the other one is x minus y equals 0. So now you have some good relationships, don't you? The first one says what? X could be 0. The other one says what? Y could be 0. Next one says what? X must be negative y. And x could be y. What can you get at? What can you throw out right now? These are gone, right? Why? Because these aren't in the domain of the original function, right? The original function, you cannot plug 0 into it. So we can't talk about critical points at those values. So this is not possible. Not in domain. So we have to look at the other possibilities here. So in an effort to try and keep this all on one page, I'm going to try and squeeze it in right here. Suppose, that's a symbol we use for suppose. Suppose x is equal to y, right? If x is equal to y, then I can come back up to, where are my equations? Right here. See this equation right here? If x is equal to y, then I can replace my y with x, can't I? Right there? So I would get x squared y squared equals 1 becomes, what, x to the 6 is equal to 1? Replacing y with x right there. And then take the 6th root on both sides, you get x is equal to what? Plus or minus 1. How many critical points did that just give us? 2. I know that my x can be 1. I know that my y can be, my x can be negative 1. But what did I assume here? That my x's and y's were identical. So I have 1, 1, and negative 1, negative 1. Y'all see how that worked? Now what? I have to look at this one. I just did that one, right? I need to look at this one now. What if x is negative y? So suppose x is negative y. And then go and plug it into here again. So let's replace our y with what? Negative x. I just moved the negative to the other side. And then I square it. Does it make a difference? Does it? If I replace that with negative x, I square it. It's still the same as x squared. So that's still x to the 6 is 1, which means x is equal to plus or minus 1, which means I can have 1 here or negative 1 here. But this time, my y and my x, the relationship is that they're opposites. So I could have 1, negative 1, and I can have negative 1, positive 1. And that's it. We have 4 critical points. And now we have to calculate D on each of those. Could I just leave that to you? Calculate D? Or do you want me to just do one of them? Okay, this first thing we said is, look, I'm going to assume x is y because that's part of what makes all of this stuff true, right? We came down to x is equal to y. So I said, all right, let's suppose x is y. If x is equal to y, then I can go back to this equation right here. And what if I replace this y with x? It would become x to the 4th times x squared, which is x to the 6 equals 1. Then I take the 6th root on both sides. That gives me x is equal to plus or minus 1. So I'm saying, all right, x can be 1 or x can be negative 1. But remember, if I say x is 1, I assume that y was the same thing, so the y must also be 1. I'm plugging it back in here. The difference is on this one, I still get 1 and negative 1, but the relationship now is that whatever x is, y is opposite of that. So it's negative 1. And then if it's negative 1, it's positive 1. Make sense? All right. I'll do D on one of these. Let's do D on this one. D here. So what's fxx right here if I plug in 1, 1? 1 for x, 1 for y. It's 8. Okay, what's fyy, which is this one, if I plug in 1, 1? 8 again. And then minus what's fxy if I plug in 1, 1? 4 squared. So that's 64 minus 16, positive number. Okay? And then what about fxx? It's positive. So what happens if you have positive D and positive fxx? Local min. So you do each of those the same way. And what you're going to see, here's the surface. Notice it's undefined. in a lot of places here. But you have these minimum values. Those are them right there. Kind of see them down there. We found those. All right, I'm exhausted from this idea. How about you? All right, I'm not exhausted, but you think you got it now? I will point out what to do on the next one. I won't go through the problem. If you look at your notes, can you see these over here? Can you see those? Can you make those out on your notes? Here's the picture of what's happening here. You have 4 saddle points. Here, 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 and here. And you have 1 local max that's at the origin. Or no, hold on. No, the origin is not. The origin is not. Where is that one? This one. Okay. Sorry. This one, the top one here, is a local max. The other 4 are saddles. What I would do if I were you, when you're doing this problem, when you have to find the partial with respect to x, you can treat all of this like a constant, right? And do your derivative here. And then partial with respect to y, you just do this part and then treat that as a constant. Or if you want, you can actually expand it all out first before you do any derivatives. Just multiply it all out and then go do your derivative. That's kind of up to you. This problem right here is a bonus problem. And my warning to you is that it is not as easy as it may appear, because there's something very interesting happening on this function. Let me turn it around so you can see it. There's something very interesting happening on one of the coordinate axes. Along this axis right here, there's something very strange occurring. So if you do this as a bonus, you can turn it in. Let's say it'll be due on Wednesday. I'll give you a week so you don't have to worry too much about it before the test. And it's not worth a whole lot. I think these bonuses, I'm adding like 5 points to one of your mini exams, so it's not, don't be like, it's going to change a letter grade in this class for you. But it's a good exercise, because when you look at that, look at it from the side like this, you got something really kind of weird happening, and you should see it. When you go through the work of this, it should kind of pop out at you like, oh, wait, hold on, what am I going to do with that? And there's nothing I've done today that will actually help you with it. You have to just think through it, and like, how could I convince myself what's happening along that axis? And I'm interested to see what you come up with, okay? But if you get these points right here, get all those. If you get those, you'll get some of the credit, but you don't get full credit unless you can also handle what's happening on that axis. All right? Okay, let's take a break. It's a good point for a break, right? All right, so what we looked at so far is how you would find local maximums and minimums on unbounded domains for functions of 2 variables. We calculate D, right? But what happens if we now restrict it to a closed interval? Now, immediately you should be thinking, well, wait a minute. In 2-dimensional space, yes, we have a closed interval between A and B. But if our domain's in 2D, what does it mean to be closed interval? So we need to talk a little bit about what closed sets are in 2-dimensional space. So here are some examples of closed sets in 2D. Remember, the domain is the ground, right? And we want to look at a closed set on the ground. Closed set would mean something like that circle, something like that square. These are things that are not closed. So this one is not closed because it does not include the boundary. This one's not closed because it's missing a point on the edge. And this one's not closed because it's not including part of the boundary, right? It's hard to see, but this is solid and then dotted, 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 right? So a closed set in R2 is one that contains all of its boundary points. A bounded set in R2 is one that is contained within some disk. In other words, it is finite in extent. Then in terms of closed and bounded sets, we can state the following counterpart to the extreme value theorem. So here's kind of like what we had earlier. Remember, in two-dimensional space, we said that to find the absolute max and min, we tested the endpoints, but then we also found out where the derivative was 0 and undefined, right? Or have you zoned out enough or too much by this point, or are you still here with me? This is what I'm talking about, right? Okay. When we in 2D, we're trying to find the max min. We look at the endpoints, and we look at where the derivative is 0 and where it's undefined, possibly. Now we have something that's similar to this with functions of two variables. And it is saying that in order to find the absolute maximum and minimum values of a continuous function on a closed bounded set D, so some set that looks like something like this, then we will find the values of f at the critical points of f in D. So what do we think critical points mean? Where our partials are 0, right? Instead of derivative 0, it's going to be where our partials are 0 or possibly undefined. But can we have cusps here? We haven't talked about that too much. Can you have a point? You know, think of like a cone, right? That top point, what's happening there. But we will look at the critical values. Then we will look at the extreme values of the f on the boundary. That's like looking at this function on the endpoints. We have to look at our function on the boundary. That's the hardest part of the entire problem, is doing that part right there. And then the largest of those values from these two being compared. So same thing we did before. Compare endpoints, compare the critical numbers, compare them. Biggest one's the absolute max, smallest is the absolute min. So it's very much the same as what we've done. Understand that part? Was that in your notes? Okay, this is all out of the book. Sorry, this is, well, you can find the page. It's in there. Are you looking at it right now? This is in 11.7 still. So it should be a couple of pages in there. 674? Okay, so this is all there if you need to look at it. All right, so let's first try and get our heads around what's happening here. I want to find the absolute maximum minimum values of this function on a closed triangle with these vertices. So the big difference here now is that instead of just giving you find absolute max min of a function and I don't give you a domain, now I'm saying the only things you're allowed to plug in must live on the closed bounded region formed by those points, the triangle formed by those points on the ground. So here's just that surface if I do not restrict the boundary, okay? Or if I do not restrict the domain at all. There's the surface. What we're going to do, though, is we are going to restrict the surface. So here's the domain in two-dimensional space. And what were the points? They were 1, 0. So imagine going out 1 and then don't go up or down. So that's 1, 0. The next one is 5, 0. And the next one is what? 1, 4? So there's my triangle in 2D. If you take every point in that triangle and plug it into the function, it'll go up to somewhere on that surface, right? And so what you get, let me bring my surface in here. You see my surface, and do you see the domain on the ground now? See that domain's down there? If you just take those points and plug them into the surface, you get that. So what I can do is I can bring the surface out of here so you can see it a lot better. The greenish here is just the points in that triangle plugged into the surface. See, if I turn it, it's exactly on top of it. Understand? We are trying to find the maximum and minimum values of that green thing. Highest and lowest points. So, do you agree that for the green part, the inside of the green part, that's just part of the bigger surface? Right? That's just part of the bigger surface. So if there is a maximum or minimum inside the green stuff, we should be able to find it the same way we found it before we restricted domain, right? We should have a critical point, and we should be able to compute like where we would get like a D. Yes? But what about the edges? How do we account for the edges? I mean, it's a tough thing. How can you say plug in, like in 2D, we plug in the endpoints. That's no problem, right? Just plug in the endpoints, we're done. How do you plug in an edge? That's the challenge. So look, imagine, first of all, that we look at this edge right here. You see that edge right there? I'm going to call it line 1. If I plug just that line into the function, do you see that you get just this front edge? Okay, you see that? Pardon? Well, that would give you this endpoint, and it would give you this endpoint, but it wouldn't give you anything in between. Okay, so if I plug in this line, just that line, then I get just this edge. And if I pull out, let me pull the region out of there, then it's just a line, right? That's all it is. If I look at it from the side like this, it's just a line. And we should be able to figure out where the maximum, and minimum points on that line are. They'll be the endpoints, right? But that's just for that line. Let's take a look at something else. What if we don't do that edge? What if we do this edge, the diagonal of the triangle? If we do the diagonal of the triangle, it creates this back edge right here. Okay, you'll see that. I'll pull the region out. And what type of shape is this? It's a parabola. And we should, well, it looks like a parabola, right? And we should be able to find the maximum of that. What I'm trying to get you to see is that along each edge, let me bring that first edge in here. There's that blue edge. I think I'm going to take the domain out so you can't see the domain. Along one edge, I get a line. Along the other edge, I get some curve. And then along the third edge, this red one, I get another line, it looks like, right? So along each edge, I have a continuous function on a closed interval. Right? Ignore everything except that blue line. That is a continuous function on a closed interval. We can find max and mins of a continuous function on a closed interval using Cal1 methods. So this problem is going to actually, each edge we go along is going to be its own Cal1 problem. That makes sense? And we're going to move along all the edges. Once we move along all the edges, we figure out the max and mids along the edges, and then we compare it to anything that we found inside, and the biggest is our max, the smallest is our min. These are extremely long problems, all right, because it's a lot of work. So shall we? Yeah. We have no choice. I believe I included the work for this one, didn't I? It's in your notes? Yes? All the work is in here? All right. So let me try to go through this. Do you all understand geometrically what we're doing, though? All right. Oh, wait. Maybe I didn't. Did I? Oh, there it is. I was looking for it. All right. Here we go. So the first thing, I hate to read something that's in front of you, but I know you can read, but I want to clarify anything if you have any questions. So first, let's use the second derivative test to find the local max and mins of the function. And that means let's find the local max and mins, not acting like there is no restriction on domain. Just where do highest and lowest points occur on this thing? We can only consider points inside our region. So we take the partial with respect to x, we get y minus 1. Y'all agree? Take the partial with respect to y, we get x minus 2. We set each of those equal to 0, and we get x must be 2 and y must be 1. Yes? Is this in our region? You'd have to look back up at that triangle. Is the point 2, 1 in here? It's right there, isn't it? Right about there, 2, 1. That is in our triangle. What if it was not in our triangle? We wouldn't even consider it. Okay, but we will have to consider that point. So That part's done. We aren't even going to calculate D, okay? We aren't going to calculate D. All we have to do is plug that into our original function later when we're comparing it to the other things. So no D computation is required. All right, so the only critical point is 2, 1, which is in our region. So if we plug it into the original function, we get 2, 1, 1. That means I plugged it into this, right? That's a potential maximum or minimum. Here's the hard part. We now need to consider the boundary of the region. So let's look at L1. L1. At least for this first example, I really got to make sure you all understand what I'm doing. Okay, what were those points again for the, it was 1, 0, right? 2, 3, 4, 5, 0, 1, 2. There's my triangle, right? If I decide that I'm going to call this side right here L1 of my triangle, any point that lies on that line has to satisfy what? Every point that lies on that line has some x coordinate, right? But what's the y coordinate always have to be? It always has to be 0. And what's the restriction on the x coordinate? Must be between 1 and 5, right? Everyone agree with that? So what am I going to do with those? What I'm trying to do is plug those values into the function, right? See, what happens if I plug a point like that up into the function? It draws something, doesn't it? What does it draw? Well, what I need to do is ask myself, what happens if I take a point that looks like that, x0, and plug it into the function I was given? So the function I was given was, what, 3 plus x times y minus x minus 2y? So that'll be 3 plus x, which is x, times y, which is 0, minus x, which is x, minus 2 times y, which is 2 times 0. Does everyone understand what I'm doing here? This gives me what? 3 minus x? 3 minus x? Yes? So let me go back to what I had here. That's what I'm trying to say here. On L1, we have points that look like this. The x values are stuck between 0 and 5, or between 1 and 5. If we plug them into the function, we get this right here. So that's this blue thing. Take all this crap out of here. This blue line right here, the diagonal, that's part of that region there, that's that edge. That has that's basically a line, and it's the equation of that line is 3 minus x. And so what I need to do is find the maximum of that function. We need to just find the maximum and minimum values of 3 minus x on a closed interval. So how do we find the maximum of a function on a closed interval? Take its derivative, right? Set it equal to 0. Well, what's its derivative? -1, right? That's never 0. So we don't have any critical points. So what we've done is we have a function. We said, was there anywhere in there where the slope of the tangent line was 0? And we said no. So the next thing we have to do is check the endpoints, right? We're back in Cal 1 doing this now. So now plugging in the 2 endpoints, but the endpoints were 1 and 5. We plug those into the function. Plug 1 in here, we get 2. Right? And then if we plug 5 in there, we get -2. Do you all see that? So if we write them as ordered triples, when we plugged in 5 for x, And 0 for y. Why is it 0 for y? Because we're on L1, right? And L1 always looked like x0. So 5, 0, that spit out -2. And then if we're at 1, 0, it spits out 2. Does that make sense? Now what we need to do is move along and go to L2 and check there. So when we're on L2, and I believe I called this one L2. I don't like my L2. There's L2, all right? How did I come up with what I said here in the notes? Because I said on L2, the points look like x, negative x plus 5. Where the hell did I get that from? Yeah, this L2 is a line, right? And if you extend that line up and down like this, that's right. You can look at it this way. Watch. If this is a point, this is the point 1, 4, right? And this is the point 5, 0. Can you tell me what the slope of that line is? y2 minus y1 over x2 minus x1, right? And you would get what? -1? And then you could find the equation of the line. If you find the equation of the line, you could use this. Y equals mx plus b. You could replace m with -1. I'm reviewing like college algebra stuff right now. I shouldn't be doing this. And then I replace x with what and y with what here? Any point on the line, right? So how about 4, 1? That lives on the line. And so you get b is 5. So you get your y-intercept. You could probably visually confirm that that's what's happening. But the point is that it's a line. Everyone in this class should be able to come up with the equation of the line. And the y-coordinate is the equation of that line. So what do we do with that? We have to come up with a restriction. What's our restriction on x here? If everything on L2 looks like this, our x is still restricted between 1 and 5. And then we say, well, what's happening when we take points that look like that and plug them into the function? So I've got to take f, and I've got to plug in x for x and -x plus 5 for y. And do I show that? I don't show that work. Do y'all realize what I'm doing, though? I'm plugging in was it 3 plus x times y, but y is -x plus 5, and then minus x, and then minus 2 times y, but y is -x plus 5. And if I clean all that up, right, do all the algebra on that, I get this quadratic right here. And so now we've reduced this to a Cal 1 problem. I just need to find the maximum minimum values of this quadratic function on a closed interval 1, 5. So the first thing I do is I take its derivative. The derivative is -2x plus 6. I set that derivative equal to 0 and get a solution of x equals 3. Now plugging in 3 and the endpoints. What were the endpoints? 0 and, shouldn't that be 5? Is that a typo? I believe that might be a typo. Wait a minute, hold on. Pardon me? Now plugging in 3 and the endpoints 0 and 2 into this. Why did I put 0 and 2? This should not be right. It should be what? 1 and 5, right? Please change this. Change that in my notes too. Did y'all see that? Okay. So if I let x be equal to 3, x be equal to 1, x be equal to 5, I get these respective values. And that will allow me to get the order triples. So I have 3 points along that curve. And that corresponds to, take out my surface here, take out that L1. There's the curve right there, the parabola. I found the 2 endpoints, and then I found that maximum point. Okay? Then the last one. On L3, we have a different sort of format for our points. So I'll look at that last L3. If L3 is this line here, all points that live on that line have to have an x-coordinate of 0 and a y-coordinate of whatever y is. And then what's the restriction on y? Y is between 0 and 4. And then you plug the points 0, y into the function. And when you do that, where is it? Right here. Wait, was it 0, y? Hold on, it wasn't 0, y. That was oversight. That's 1, y, right? Remember where this point was. This point was to the right 1, right? So the x-coordinate is always 1. The y-coordinate can vary between 0 and 4. So 1y, not 0y. So we take those. No, our restriction is still 0. The y is restricted. See, the y is the up and down, right? The y is still restricted between 0 and 4. But if I'm at this on this line, my x-coordinate is always 1, because the whole line has been moved over to the right 1. Plug those into the function, and when you plug them in the function, you should get 2 minus y. And this is just a line. We need to find the maximum min on a closed interval, 0 to 4. Just like before, we take the derivative, it's never 0. Plugging in, we get these points eventually. And then we compare all of them together. And what we're looking for are the z-coordinates. So the smallest z-coordinates I have are -2. It happens at 2 different places. The largest z-coordinate I have is 2, and it happens at 2 different places. And that should correspond to the picture. Looks like our highest points were right here, and our 2 lowest points were right there. Yes? What if the region on the ground is a circle? Great question. If it's a circle, there's several different things we could do. You could always break up the circle into different functions, like so it's still a function, or you could convert everything into polar coordinates. Either way, but let me see. I don't think I give you a circle, do I? Yeah, we're going to build up to that, to more complicated regions. Let me see if I have one here. Here's one. This is a circle, or part of a circle. Let me see. Do I have this one worked out? Yeah, I've got that one worked out. Okay, let's look at this example. I don't think I'll work through this one. This one, I have our function here, and I just wanted you to see this notation here. We're restricting our domain to all ordered pairs where our x is between 0 and 3 and our y is between 0 and 2. So all points where your x is between 0 and 3 and y is between 0 and 2 is a rectangle. Okay, it's a rectangle. And so what we're doing is we're taking that rectangle and we're plugging just those values into the function. Here's our surface. Here's the actual region. If I pull the surface out, you can see again that that's the part we're looking for. We're looking for the highest and lowest points there. So first we do the calculation, or we do the like the second derivative test part that we did in the previous section, or previous part of today's class. We do that first, and then we'll come in, we'll call this L1, we'll go along this line. Looks like when we go along this line, we're going to get some sort of like parabolic shape. Then we're going to go along line 2, which looks like that back edge is probably going to be a line. Would you all agree? And then we go around that one. That looks parabolic, doesn't it? A little bit. Right here. And we go along that final edge, it looks like a line also. So without going through and working and drawing all this out again, we take our partials, we get these two, we set those equal to 0, we get one critical point, which is 1, 1, which is in our region. So we'll have to check that point, 1, 1, 1. At the very end, we'll compare it with everything else. Now we have to consider the boundary. Along one boundary, we get that our x-coordinate is 0. Our x-coordinate is x, and then our y-coordinate is 0, and our x is bounded between 0 and 3. Are y'all okay with that off this picture? Off this line right here? X is between 0 and 3, y is 0. What about this one on L2? X is 3, y is between 0 and 2. Up here, x is x, right? So x is between 0 and 3, and y is 2. And then here, x is 0, y is between 0 and 2. Okay, so I'll let you read through that one. I'm trying to see if there's one that I did not include work for. This one. Okay, let's try this one. Well, do you feel like you need to see another one of those, like worked out, like one of these? No? You're not concerned about this one that has a different region on the ground, like this is a half circle or quarter circle? Okay, if we're not going to do this one, let's just talk about the lines at least. Or L, we call it L even though part of this is not a line. This one right here, tell me the restrictions on this line. Y is 0, y is 0 and x is between where and where? Where are you getting that from? Yes, this right here is a circle, right? So this was saying we had to have a circle radius what? Radius is square root of 3, right? And then our x has to be bigger than or equal to 0, which means we don't want to be over here. And our y has to be bigger than or equal to 0, so we don't want to be down here. So it's just basically this first quadrant quarter circle. So our along that first line there, L1, our y was 0, and our x is between 0 and what? Square root of 3. Now on L2, right there, we have to look at these as ordered pairs. To get to anywhere on that, we can have x is x, right? And y will be something, right? How about just solving this equation up here, right here? Make this an equation and solve for y. So move the x squared over, take square root. And you can see in my work, that's what I did right here. Our x is x, and our y is the square root of 3 minus x squared. Our x is still bounded between 0 and root 3. We plug this into the function, and when we do that, luckily it comes out to be a cubic function. And then to find the maximum of a cubic function, we take the derivative, set it to 0, we get answers, we check endpoints. Okay. I think what we'll do is what we did last class. I think we'll do like another, y'all like that quiz at the end? That's fun stuff. We'll do like a quiz you can work together on. No, you don't like that? on one of these? How about this? We're going to do the volume problem, but how about I'll let everyone work together on number 8 on your mini take-home exam in class today. Has anyone done it yet? Oh, wait, not number. Yeah, number 8. Yeah, not right now though. Hold on. Let me finish this up. It's way too early to start that. Because everyone seems like they understand it, but until you actually go and do one, it's a different thing. So find the volume of the largest rectangular box that can be inscribed into the ellipsoid given. The volume of the largest rectangular box that can be inscribed into the ellipsoid given. Somehow this is connected to what we're doing today. So what I have in this program is I have the computer's calculating the volume of this rectangular box thing in here. Do y'all see the ellipsoid? Okay, it's inside there. Inscribed means that it's the corners, right? The vertices of the box are just touching the edges or the surface of the ellipsoid. So if I adjust the dimensions of that box, the volume changes. I can make it really wide, right? I can make it very tall, but the taller I get, the more narrow it has to be, right? What are the dimensions that give me the most volume? So there is an optimum solution to this that gives me the biggest box in there. And what is it? You could do this in Cal 1, but we're going to do it in Cal 2 now, all right? So whenever we have these optimization problems, what we did was we tried to figure out what function it was that we were trying to optimize. And in this case, what is it that they want? The maximum what? What did I ask for here? Did I not? Oh, I didn't put the problem. Oops. Okay, well then, sorry, that's the problem. Find the volume of the largest rectangular box with edges parallel to the axes that can be inscribed in this ellipsoid. So what is it we're trying to find the maximum of? The maximum what? The biggest box I can put in there, yes, but not biggest, how do you mean biggest? Surface area? Volume-wise, right? We're trying to find the maximum volume of that box. So what we need to come up with is an equation or a function that represents the volume of that thing down there. So let's try and get it. So let's say we're in three-dimensional space. I have X, I have Y, I have Z. And I draw a rectangular box in there so that the center of the box is always the origin. Then the top corner of the box, let's say if I go out a certain distance X, and then I go out a certain distance on the Y-axis, then I go up a certain distance on the Z-axis, that could be one edge of the box, right? One corner, one vertices. And then what I would have to do is imagine going all the way back, and then across, and then over. And then how far down do I go? Let's say we go below the XY plane. What I'm trying to get you to see here is that the way that I'm going to draw this box is that my XYZ is only going to create a portion of the entire volume. What portion would it create? Do y'all see what I'm saying or not? Am I confusing you with this drawing? No answer. The question I'm asking is, what is the volume of the entire drawing I have here? If I went out X, I went over Y, so I went out X, I went over Y, I went up to a point, and I said, that's one of the corners. To draw the rest of it, I have to go back. Don't I have to punch through the YZ plane there to go backwards. And across, I punch through the XZ plane to go on the back octant, and then come back across. How many of those black rectangular boxes do I have in the total box? I have 8 of them, right? There's that one. There's that one. There's one in the back corner, there's one there, and then there's one on the bottom, one here, and one here, right? That's what I have. I have a total of 8. The dimensions of one of these, right? The dimensions of one of those are what? X, Y, and Z. So the whole thing is 8 X, Y, Z. Agreed? Okay, so the volume function that I'm trying to optimize here, the volume, is if I know what X times Y, if I know what X, Y, and Z are, I can tell you what the volume of this whole thing is. Oops, I forgot the 8. So if you give me that point, that vertices, which is the X, the Y, and the Z coordinate, I'll multiply all that together times 8, and that'll give you the volume of the whole thing. And depending on what X, Y, and Z are, it'll change the volume of the box. But the fact that this thing has to live within that ellipsoid means the X, Y, and Z that I pick also have to satisfy the equation of the ellipsoid. Do you agree? So what's the equation of the ellipsoid? Well, I have to go up here because it's not in our notes. This right here. So let me jot that down. 936, 436. 936, 436. That's the equation of the ellipsoid. Now what I can do here is I can take this equation that has 3 variables in it, and I can solve it for Z, and then take that and plug it into my equation for volume. If I do that, I will have a new equation with how many variables? V equals, and V will be in terms of 2 instead of 3. So solve this for Z, and what do we get here? 4Z squared equals 36 minus 9x squared plus 36y squared. Divide everything by 4. That's a minus, isn't it? Sorry. And then take your square root. Now, I'm not going to do plus or minus. Why? I'm going to assume it's in the first octant. So I'm going to assume that my Z coordinate is positive. Is that all right, everyone? Take that, and now go back to your volume, which was up here, and replace Z with this. And what we get is a new volume, but that new volume only depends on what 2 things? X and Y, so I'm calling it V of XY. Now I'm looking at it like a function of 2 variables. It is 8xy times Z, which is 9 minus 9/4 x squared minus 9y squared. Can I pull a 9 out underneath that root of everything? Yeah, and then 9, and then it'll come out as a 3, right? Once it comes out of the root. And then multiply it times that 8 in the front. So 24xy square root of 1 minus 1/4 x squared minus y squared. This is my volume function. So what do I want to know about the volume function? What is it that I'm trying to find? Where does it have a maximum, right? Well, we have a function of two variables. How do you find maximums of functions of two variables? You have to ask yourself the next question. Is it on an unrestricted domain or is it on a restricted domain? It is restricted. What's it restricted between? The ellipsoid, right? But you need to be able to come up with some restrictions, though. If you're going to restrict it, you need to be able to define the closed, bounded region that it's restricted on. Can you describe that region to me? Look at it over here. Isn't this it on the ground? Isn't this it? Something like this? Now, I mean, it's not exactly this one, but think about this. Your ellipsoid hits the XY plane, doesn't it? In a circle. And you're only looking in one octant of that circle from the top, right? So the question would be, what is that? What is the circle where it hits? How do you figure that out? Say it again. Right here? Yeah, when you think about where does this ellipsoid hit the XY plane, you're really saying when is what? When that thing hits the XY plane, you're saying when is Z 0, right? When is Z 0? If Z is 0, or what happens when Z is 0? When Z is 0, what do you have? 9x squared plus 36y squared equals 36, don't you? So I'm trying to get at this here. When Z is 0, we get 9x squared plus 36y squared equals 36. What's wrong with this? Divide everything by 36. X squared over 4 plus y squared equals 1. Is that a circle? It's an ellipse, right? That's an ellipse on the ground. Can we define an ellipse easily? Maybe. I'm looking on the ground here. Here's X, here's Y. I'm only doing this because it's been suggested that perhaps we are in a closed bounded region, right? It looks like we have part of an ellipse. Which side's bigger? Which, is it longer than it is wide, or is it wider than it is long? Is it taller than it is wide? Wider than it is tall? Wider than it is tall? So it goes like this. Hits where? Do you know where that hits? 2. And here, 1. Now the whole thing is an ellipse, right? That looks like a circle, kind of, doesn't it? Is that a closed bounded region? Well, can you include the edge? Can you include the edge there? Can you include all these edges? What's your volume going to be if you go on L1? If you go on L1 right now, what's Y? On L1, what's Y? 0. So what's your volume? If Y is 0, your volume is 0, right? If you go along the other line, I'll call that L1. Let's call it L2. Let's call it L3. If you go along L3, then what's 0? X, and so your volume is what? 0, right? What about on L2? Wouldn't you have to solve this for Y over here? Yes. But on L2, what's Z? I mean, that's when your ellipsoid hits the XY plane, right? So what's z there? 0. I mean, the point of this is, what I'm trying to get at, is that you do not have to look at the closed bounded region, because along the region, your volume is 0. So we don't have to consider it. All we have to consider is the thing we did in the beginning of class. So we could just look at this as being completely unbounded and just figure out where the local max and mins happen. Because we can all agree that on the boundary, the volume is 0, and that's not what we're looking for, right? It may be the minimum value, but we're not looking for minimum, we're looking for max. Hope that makes sense. So how are we going to find the max min stuff here? What do we have to do with this? What's our method? Calculate D. So you're going to need Vx, Vxx, Vy, right? Vyy, and do you see how ugly these are going to be? Do you see the ugliness here? What's the partial derivative of that with respect to x? 24y, square root of the junk, right? Product rule? Doing here product rule? Plus the derivative of the square root of the junk is 1 over 2 times square root of the junk. What's the derivative of the inside of that with respect to x? Negative 1/2 x. And then times, finish off product rule, 24 xy. Now, we want to think through this a little bit. Do we even want to go after Vxx? I sure as heck don't want to do it right now, right? If we can avoid it, because that's going to be a hell of a derivative to take. So I'm just going to hang tight. I'm going to go Vy first, because don't I have to set Vx and Vy equal to 0? And what if I only get one answer? I mean, shouldn't there only be one maximum? Shouldn't there? I mean, there should only be one point where I have a maximum. Shouldn't get like 5 points. So maybe it's possible that if I just look at Vx and Vy and set each of those equal to 0, I'll get a solution. It'll be one solution. I will know that that's got to be the only place it can happen. So I'm thinking ahead of, instead of being like robotic about it and being like, oh, let me just do this, then this, and this. I'm trying to avoid some work. What is going to happen when I do derivative with respect to y? Almost the same, right? What's the difference here? Negative 2y, right? And then 24xy. You'll see that's same. That's derivative with respect to y. It's derivative with respect to x. How do we want to go about this thing? Set those equal to 0. So let's say I set this one to 0 here. I would have 24y square root of the junk. Let me see, what does that clean up to be here? Is that negative 6xy over square root of the junk? Everyone agree? Negative 1/2 times 24 is negative 12. Divide that by 2, we get negative 6. We still have, x squared y, right? On top. If I set that to 0, I can get a common denominator. How do I get a common denominator between these? Multiply the root here on bottom and top, which means that the root's going to go away. So I'm going to have 24y, and then the root goes away. So what was actually under there? Is it 1 minus 1/4 x squared minus y squared? And then what's still up there with it? Minus 6x squared y. Then all over the root equals 0, but then I don't have to look at the root, do I? Because it's a fraction. So that. Should we distribute this through? 24y minus what? 6x squared y, and then minus 24y squared minus 6x squared y equals 0. Oh, y, yeah. That's y cubed at the end here. Some of this stuff goes together, right? How about this? 6y. How many x squared y's are we going to have? Oh, I did not mean to do that. I want to divide everything by 6 first. So 4y. How about negative 2x squared y, and then minus 4y cubed equals 0. So I put negative 6x squared y, negative 6x squared y together, get negative 12x squared y, and then divide that by 6, and I get that, and then these two here divided by 6. We good? That's all just the first one. So I'm going to come back to that. Let me set Vy to 0. If I set Vy to 0, my Vy is this part. How does this simplify here? I get these two to cancel. So I get negative 24xy on top there. Can I put them together now? Get a common denominator and put them together? So it's 24, but instead of, I'm going to have 24x, right? And then times this, and then what? Instead of this, I'll have what? Be minus or plus? Still have a negative here, right? So minus. So we'll have, see if I can get this all together. I'll do it in black. 24x times 1 minus this, and then minus, what do we say, 24xy? xy squared. Yep. Equals 0. So I'm setting my derivative here to 0. Distribute through. Does this seem like it's okay or not? Can we put any of that together? And the last two here, negative 48 of those. And then can I divide everything by 6 again? So I get 4x minus x cubed minus 12xy squared equals 0. I'm sorry? What did I do? Oh, yeah. Thank you. All right, so we have these two equations, right? This one and this one. So how do we set those? I mean, how do we solve those? How do we, do y'all see what we can do on these? Anything? Any suggestions? So you mean solve one of them for something and plug it into the other one? What do you want to solve for? You want to solve for x up here? Plug it in here? Just trying to figure out what y'all are thinking. Do you all have any questions as far as the setup of this and what we're actually doing here? And Does this look like it's not just a clean, simple, easy? I mean, it looks like there's some work to be done here to get those, right? So your options are just try and solve for one of these and plug it in here, or maybe solve for one of the variables here, plug it in there, or you can set them equal to each other, right? Does setting them equal to each other give you anything? What's that? Graph? Ooh. Well, we have to pick a way here. I mean, we have to pick some direction. So why don't we try equal to each other and see where it leads us? Right? That's equal to each other. Any of those like terms at all? Nothing? So what the heck would you do with that? I mean, is there anything we can put together and maybe factor stuff out? You could do factor a y out this side, factor an x out this side, right? But then factoring here is not really going to help because then we can't move things around because things are trapped by factoring. So this looks like it's possibly not a good approach. So, which leaves us, I mean, this is kind of a question. Should I keep going here? Or should I go back to this and try and figure something out here? So at what point do you concede? Or do you concede? You'll agree with that? Just factor out a y? Yeah. That means y equals 0 or 4 minus 2x squared minus 4y squared equals 0. Well, y can't be 0, right? Y is 0, you get volume is 0, so I don't care about that. Over here, anything on this side? Like I was saying earlier? Good. Could you get x or y by itself here? Is that right? But I mean, basically it comes down to plus or minus, right? This 2 minus 2y squared. Absolutely, you can ignore the minus. So we have some idea of what x must be, right? Could you do the same sort of thing or take that and plug it back into the other one? What's the other one look like? This one right here, right? Let me throw that one down here. So what could I have done here? Factor x, right? You're left with 4 minus x squared minus 8y squared equals 0. Now x again we said couldn't be 0, so we don't have to worry about that. So we could have said 4 minus x squared minus 8y squared must equal 0, which means that x squared had to be equal to, hold on a second, x squared had to be equal to 4 minus 8y squared. Now hold on a second. Yeah, well, before we square root, why don't we come back up here? Didn't we say earlier that this x squared had to be that, and now we're saying x squared has to be this? Right? So don't these have to be equal to each other? So I have 2 minus 2y squared has to be equal to 4 minus 8y squared. Let's see if that makes any sense. 2 minus 2y squared has to be equal to 4 minus 8y squared, which means what? Can we solve that for y? Should be able to, unless it comes out to be non-real numbers. So how about we add 8y to both sides? I get 6y squared. I subtract 2 on both sides, I get 2. And that means y squared is 1/3, which means y is what? Right? I rationalize just for fun. I'll leave it this way. All right. Okay, so that means that that's what y is. I didn't look at the negative. And if I know what y is, can I get x? I should be able to. And if I get x, can I get z? Yes. So we're pretty much here, all right? I don't think I'll go back and get x because you can plug it in. Does this kind of give you some indication of some of the algebra that you may run into? I mean, just that it may look discouraging, but you just have to keep trying until you get to somewhere. Hope that you get to it. Let me see if I can give you the solution here. I'll just look at my answer here. I think I have the optimum solution on here. So the y value we said was 1 over square root of 3, right? So 1 over square root of 3 is y. X should come out to be 2 over root 3. And then from that, you can get z. Okay? All right, let's do that problem now. And in class, you've got 40 minutes, right? Wait, 30 minutes. I always think we end at 40. 30 minutes. See how you do on number 8. Now, you still have to turn this problem in next Wednesday, written down on, with your exam. All right, I said this is due next Wednesday. Okay, so you still have to turn number 8 in on your own, but I'd like for you to work on it in here. And you can ask me questions and help each other out. I will ask you, I've noticed on the first 2 mini exams that there are a lot of people still trying to do all their work on the mini exam. Like, just do your work on separate paper, okay? I prefer it to be all separated in order, stapled at the end. Okay, let's hit the lights.